Hi everyone, this is Dr. Hopkins narrating the next of our videos in Chemistry 472. And this video is about the temperature dependence of kinetics, chemical kinetics, and reaction rates. So the first thing we're going to start with is what you used in general chemistry, which is the Arrhenius equation to describe the temperature dependence. So we considered a general rate law. In this case, I just have one component, but the rate depends on the concentration and the rate constant. But we know that concentration really shouldn't change a whole lot as we change temperature. So all of the temperature dependence is going to be included in the rate constant. And so we can write the Arrhenius equation. We write the rate constant is equal to A, some pre-exponential factor, and then it's the exponential of the activation energy over RT, where R is our gas constant and T is the temperature in Kelvin. So what are these activation energies and pre-exponential? So this is the kind of classic reaction coordinate diagram. So you have reactants and you have products. These are the thermodynamic energies. And basically you have to overcome some activation energy in order to get from reactants to products. And so the activation energy by definition is just a minimum kinetic energy to form products. The pre-exponential, a lot of it depends on how many components are involved in the reaction, but it's basically a measure of the rate of collisions. So if you want to think about our original expression, K represents a successful reaction. So every time something that collides with enough energy, we get success. Okay, but we can also linearize this equation. It's what you did in general chemistry, where we're looking at the natural log of K versus EA over RT, which you can then plot the natural log of these rate constants versus 1 over T, and then the slope gives you the activation energy of that reaction, and the y-intercept gives you that A, that pre-exponential factor. So that was how we describe temperature dependence in general chemistry, and it works. It's a very simple two-parameter model. All right, so what we're going to talk about now is something a little bit more complicated. So let's do activated complex theory, so to describe temperature dependence. So we're going to specifically design, although it's very similar to Arrhenius, we're going to specifically design a transition state. So we have two components. We're going to have a bimolecular process here, at least for the purposes of generalizing this. And these two components must come together, form a bond, and form this this transition state, or an activated complex. And then once they do that, they can move on to products. So we have to have enough energy to form the right transition state that leads to products. And then we have all of our rate constants associated with this process. So this looks very similar to a pre-equilibrium mechanism we described before. So the first step is reversible. If we think about it as a pre-equilibrium, we can set up a equilibrium constant, so this K double dagger. Now it's not an equilibrium, it's a kinetics event where we have our transition state over the concentrations of our reactants. And so then the formation of the transition state leads to products. So K2 is related to our rate of the reaction overall. And so we can describe the temperature dependence as this Kb is the Boltzmann constant, it's 1.38 times 10 to the minus 23. So Boltzmann constant times Avogadro's number is the gas constant, divided by the Planck's constant, H, and then we have temperature in Kelvin, and we have our K double dagger for our formation, or the equilibrium of forming our transition state. So let's keep with the kind of thermodynamic analogy, even though we're not doing thermodynamics. And so let's apply a delta G double dagger to this particular reaction. So a delta G double dagger would be minus RT natural log of K double dagger. And we also can think about delta G as delta H minus T delta S. So let's apply this to our kinetic situation. So now we have our K2. We've substituted in for K the e to the minus delta G double dagger over RT. Now let's plug in our enthalpy and our entropy terms. And so then the rate constant for formation of this product is this temperature dependent term with respect to the enthalpy of the reaction, or enthalpy of the formation of the activated complex. And the entropy of the formation of activated complex. This is called the Eyring equation. Now, just like the Arrhenius equation, we can linearize it, if you will, take the natural log, and then if you wanted to plot the natural log of k over t versus 1 over t, your slope has your delta h over r, delta h double dagger, and your y-intercept contains, among other things, the delta s double dagger. And what do those mean? So basically, the delta H, or the enthalpy of the enthalpy of this particular reaction, or enthalpy of this formation of the transition state, is related to the kinds of bond breaking and formation in the transition state. A direct link to, if you will, we could take experimental, and then we have delta H. We could calculate which bonds are breaking and forming to form a transition state that goes to our product. The delta S double dagger is a little bit harder to describe because it's much like entropy. It's not as simple as just bond breaking and making. So everything that goes into the entropy of forming that transition state. So if we're in solution, how does the solvent cage have to rearrange to accommodate the transition state to the product? The number of species you're forming. I mean, where are we getting our entropy from in this process? And that's that delta S double dagger for our activated complex. And both of those lead to a particular or important, leading to a particular reaction taking place. Okay, so the relationship between Arrhenius and Eyring. So as long as we know the molecularity of the rate determining step, we can relate Arrhenius and Eyring parameters directly. So we could use the activation energy to solve for our delta H. We can use the pre-exponential factor to solve for our delta S. So for situations we're in solution, this could be unimolecular, bimolecular, it doesn't really matter, or unimolecular in the gas phase, the activation energy is just delta H double dagger plus RT, and then our pre-exponential factor is related to our delta S. So we have, and these E's are the natural log E, so the 2.13 or whatever it is. And then if we go to a bimolecular gas, in the gas phase where we don't have any solution, we don't have solvent around, so then the activation energy is delta H double dagger plus 2 RT. And then our A, we have an E squared term, but it relates also to the delta S. So here we can go back and forth between the two temperature dependent models. So until next time.